Okay, it's 10:40. We shall start. Good morning, everyone. And today we'll continue talking about electric potentials. Well, this topic is not going to be on the midterm. As announced, the topics of the midterm are Coulomb's law, electric fields, and Gauss's law. But everything after Gauss's law won't be there. We started talking about electric potentials, and we have not defined what an electric potential is. So far, we discussed that a system of interacting charges has got some energy associated with their interactions, just as a reminder, there are lots of examples of manifestations of those energies of interacting charges. The most obvious example is a battery. A battery is a device that transfers charge from one of its terminals to the other, and when doing so, it changes the energy of the charges stored in it and does work. Whenever we talk about chemical reactions, atoms in different chemical compounds have got different energies exactly because of the different energies of the charges there. And when chemical reactions occur, they occur with a release or absorption of heat, that is, release or absorption of energy. That's exactly because of the change of the electrostatic energy of charges in the chemical compounds. Another well-known example is a lightning bolt at discharge in the atmosphere, or any discharge in the air. Just when you see a spark, that's charges moving rapidly through the air, releasing energy. And at the end of the previous lecture, we derived a formula for the interaction energy between two charges. This is the formula. We've got two charges, Q1 and Q2, distance r apart, and this is their interaction energy. Well, K is the same constant that we have in Coulomb's law, and to an extent it resembles Coulomb's law, except we've got the first power of r here in the denominator and not r squared. And depending on the sign of the charges, this energy can be positive or negative. So this equation here applies to all signs of charges. Does that make sense? Are there any questions so far? Well, that formula may look a little bit familiar, maybe even from the previous class from Physics 5a. It resembles the energy of two gravitating bodies, doesn't it? As it should have been derived in the previous quarter in Physics 5a, the gravitational energy of two bodies has got a similar form. Call it U grav minus some constant g, which is called the gravitational constant, are the masses M1 and M2 of the two gravitating bodies, and are the distance between them. It's quite similar, except charges get replaced by masses, and there's a different constant. Throughout this course so far, I kept saying that the forces of gravity and electric forces are quite similar to each other. You remember Coulomb's law is similar to the force of gravity, and well, because forces are similar, so are the energies. Well, the only essential difference between gravity and electric fields is that gravitational forces are always attractive, and that makes the gravitational energy of two interacting bodies always negative. The closer two bodies are, the smaller is their energy. That's a consequence of an attractive force. So they behave as two charges that attract each other. The electrostatic energy, however, could be positive if both charges are of the same sign. Well, roughly speaking, just in a couple of words, that's because if we bring together two charges, they're going to repel each other, and we've got to do work in order to bring them close to each other, and that work is stored in this energy. That's why it's positive when Q1 and Q2 have got the same sign. All right. I don't see any questions. So if anything unclear, please complain as usual, or just ask questions. And now that formula can be, of course, generalized to the case of multiple interacting charges, and therefore multiple charged bodies. Let me write here multiple charges. And well, to find the energy of multiple charges, we've got to sum up all pairwise contributions. So let's say our charges are labeled by indices I and j, and the interaction energy between two charges qi and qj will be k qi qj divided by the distance between them, rij, and the summation is carried out over all pairs of charges. Well, say if we've got 3 charges, I'm just showing this example to show how to apply this formula. So 3 charges Q1, Q2 and Q3 forming a triangle. The distances between them are respectively R12, R23 and R13. And to find a question.
Is I and j the same thing as I hat and j hat, just x and y components?
No, in this case it's just indices, just labels of the charges. So when we talk about vectors, I hat and j hat are vectors. Here I use them just as labels. Unfortunately, we are inevitably going to have some overlapping notations because there are only 26 letters in the English alphabet, and I think 20 letters in the Greek alphabet, while the number of physical quantities may be thousands, many thousands, and so inevitably we're going to have notations in which different quantities would use the same letter as some other quantities, and this is such a situation. Unfortunately, there's no way around it. And usually one understands the difference between such quantities from the context, but also if you are writing, say, a scientific paper, or also I recommend that for exams, when you introduce a quantity and introduce a notation for it, you just explain what this notation means, and then there'll be no confusion. Well, I've long wanted to start using Elvish letters for in papers, but not yet. That would a little bit increase flexibility. So to find the total energy, we've got to sum up all the pairwise contributions, of which there are 3. So the total energy of the interaction of the charges is the contribution of charges 1 and 2, like this, then the contribution of charges 2 and 3, and charges 1 and 3. And that can be generalized to an arbitrary number of charges. Yeah, so that's the interaction energy of all charges in the system. So it's true that it's the energy of their interactions for the entire system, but one's got to be careful here not to use the word electric potential, because the word electric potential is going to mean something different, and I'll explain it in the second half of today's lecture. All right, does that make sense? Well, let's do a quick example showing how to use this formula. Let's consider 2 protons, basically 2 ions of hydrogen separated by a distance of 1 micron. So that's 1 proton, that's another proton. The distance between them is 1 micrometer. So they will interact with each other, and because they've got the same sign, they're going to repel each other. And if they're initially at rest, and those are free particles, they're going to move away from each other. So they're going to accelerate, pick up some speed, and as the distance between them grows, the interactions will be getting less and less significant. And as they're far apart from each other, the interactions can be neglected, but the 2 protons are going to move with some velocity v in opposite directions. Well, the velocities must be the same because they are identical, and the system is symmetric in this sense. And we can find their velocity v after a very long time. That is when they are infinitely separated. So I'll write here velocity after a very long time. That's what we want to find. And how are we going to find it? We'll use energy conservation law. That is, we are going to say that the initial energy of the system matches their final energy. Well, in classical mechanics, in physics 5a, you applied energy conservation law to mechanical systems which have kinetic energies and potential energies. Here we are going to include the energy of interacting charges in it, which also a form of potential energy. So the initial energy of the system is Ke squared over R, according to the above formula at the top of the screen, because both protons have got the same charge E. R is the distance, 1 micrometer, directly from this formula, and they have no kinetic energy because they are at rest initially. When they're far away from each other, that's what I mean by a very long time, their interaction energy can be neglected, but they have kinetic energies. So the final energy is going to be mv squared plus mv squared half. And energy is conserved. It's not destroyed or produced. So the initial energy equals the final energy. Well, I'd like to emphasize that just an arbitrary system at any time has got both a kinetic energy and the potential energy, in this case, the energy of interaction of charges. It's just that initially the kinetic energy is 0. Just I could rewrite this in a more detailed form. The initial energy is the electrostatic energy plus the kinetic energy of a body moving with 0 velocity twice, because there are 2 of them. That equals the final electrostatic energy is Ke squared over infinity, because after a very long time, they're far from each other. I'll say that the distance between them is infinity, some large number in the denominator, and their kinetic energy. So this is 0, this is 0, corresponding to the equation just above. And well, from this equation, mv squared equals Ke squared over R, and we find the velocity in the form Ke squared over Rm. And if we plug in the numbers and do the calculation, we find a velocity of 370 meters per second. That's the velocity that 2 protons initially separated about 1 micrometer will acquire as a result of interacting with each other. Yes?
Why is the velocity 0 again?
Those are the initial velocities, and we are just given that initially they are at rest. If initially they weren't at rest, then instead of zeros we would plug in whatever velocities they have.
Wait. Okay, no, I got it. Thanks.
Right? Mm-hmm.
Can you explain the second half of the blue equation again? Why is it A is set over, that's just the after they separate?
Yeah, and we say that they got separated by a very large distance. are significantly larger than whatever characteristic distances here. So we should put some big number here. And it's the same as putting infinity, because if we put a big number in the denominator here, larger, significantly larger than this r, then this contribution will be negligible compared to this one. But I'm just saying, let's wait till they're infinitely separated.
And then the final part is you multiply both capacities because they're two perfect.
Yes. Okay. All right. So that's how we can use the energy of two interacting charges. And now we are coming to the topic of electric potential. Well, I said that it's going to be the topic of the lecture, but I have never defined it. So far, I only talked about the energy of interacting charges. And first, I'll start with a reminder of the expression for the work done by an electric field on the charge that moves in that electric field. So the work done by electric forces on charge Q. So when this charge Q moves from point A to point B, the electric field does the work WAB equal to the integral, which is an infinite sum over infinitesimal displacements of that charge, the force acting on that charge, which is QE, multiplied by the displacement dr. And a remarkable thing about it is that it's independent of the details of the path between points A and B. So it depends only on the initial and final locations, but not on the details of the path. And, well, we can see that it's proportional to the charge Q. So let's consider a quantity, which we're going to call potential difference. I'll write it down. Let's consider a quantity equal to this work divided by the charge Q. So I'll write here, define the quantity let me call it delta phi AB equal to WAB divided by Q. And it's going to be given according to the above formula by the integral E dot dr integrated over the path. Well, why does it make sense to consider such a quantity? Well, that's the work done on a unit charge by the electric field when this charge is moved from A to B. Well, from this expression, it's clear that this quantity is the property of the electric field only and does not depend on the charge. So it's property of the electric field in space. And it has this remarkable property that it depends only on the locations A and B, but is independent of the path between A and B. And well, so it's going to be a meaningful quantity because it describes how much work an electric field can do when charges move in it. And that quantity is called the potential difference between points A and B. Also known as voltage difference. Also another commonly used term. And that's exactly related to electric potential. Well, strictly speaking, one should call it electric potential difference, but the word electric is usually dropped in the context.
Sorry, so the quantity is the potential difference?
Yes, delta phi AB, that's potential difference. Uh-huh.
The interval of the vector E times dr, that's not dot product, right? It's just multiplication.
Oh, it is a dot product because we've got two vectors, E and dr, they're both vectors. And delta phi AB, that's a scalar. So we do multiply them. And to compute that integral, so we've got a path between A and B, and we compute it like a usual one-dimensional integral. So we split the path into infinitesimal pieces, and we'll say the displacement along one piece is dr, but it's essential that it's a vector because it can be arbitrarily orientated in space, and it gets multiplied by E at the respective point and the respective location, and then we sum over all pieces, sending the number of pieces to infinity. Well, I don't know if it was covered in Physics 19, sorry, Maths 19 or Maths 20. And if not, it may not be entirely obvious how to take such an integral. But so far, it's not required so long as the definition makes sense. It's all good. And that definition of potential difference, it may sound weird because we are defining the difference of a quantity, but not the quantity itself. And that's very unusual to what we normally do in physics. It's not normally we would define a quantity and then would consider its difference at different points or in different situations. But here we start with the difference. Yeah, it may look weird, but if we think about it, in all physical processes, charges will be moved by some finite displacements, and it will always be looking like the difference of some quantity, but or what could be defined strictly and uniquely is indeed that difference, because charges do not appear and disappear, they can only be moved. And in order to define the quantity and not the difference, we can just take an arbitrary point O and just assign an arbitrary potential to it. So we can say that by definition at some point O of our choosing, the potential, I'm going to call it phi O, is 0, just by definition. And then using the difference, that will define the potentials at all other points. So let's say there's this point A somewhere. then the potential difference between A and O is given by this formula here, and it's going to be phi A minus phi O, which is 0, given by the integral from A to O E dot dr. Question.
Why is it not O to A?
Pardon?
Why is it not O to A?
According to this formula, so A is the first point, the initial point, B is the final point, and it matches the limits of the integral. There's no limits in the conventional sense of one-dimensional integral. Those are just notations saying that we integrate from the initial point to the final point. And this counter-integral has got the property of the conventional integral that if you flip the 2 points, the beginning and the end, then the sign of the integral flips. So that equals minus the integral from O to A E dot dr. So one can flip them, but one's got to remember to flip the sign. And yeah, that's it's going to be an important formula. So you can't remember it in either form, from O to A, from A to O, whichever is more convenient. And, well, a question. Yeah. So we choose this point O arbitrarily, and just we can assign literally any value of the potential difference to it. And instead of 0, we can write any value if you wish, and that will define the potential at all other points. And usually, some choices for particular problems are more convenient than the others. Often, this point O is chosen to be on the ground, and phi O will be the potential of the ground, because in electrostatic experiments, in experiments with charges, usually you would do your experiment in the vicinity of the ground, and if you connect your charged body to the ground, all charges leak into it without significantly changing its potential. So it's convenient to choose the potential of the ground to be 0. Another common choice is to consider some point infinitely far away and say that the potential of the point far, far away is 0. Those are some common choices. Okay, we have defined a new quantity, and that quantity has got a dimension. So what's the dimension of potential? So the unit of potential is 1 volt. Well, that concept, that word must be familiar, because we've got the word volts just everywhere on batteries, on electric sockets, Well, if it's not, it's all right. Um, we'll practice it, and we'll review lots of situations where this concept and this unit is used. But from the definition above, we can immediately tell how it's related to some other more familiar units. So if we look at this formula for delta phi AB, the potential difference that's measured in volts, it's the ratio of work and charge. And so the units are going to be given by the same ratio. So 1 volt, and the common notation for it is 1V equals 1 joule, the unit of energy and also the unit of work, divided by 1 coulomb. So if we have an equation, then the units basically obey the same equation. Here it says that 1 volt equals joule divided by coulomb. And as I said, the potential difference is used synonymously with the word voltage. So also we can relate 1 volt to the units of an electric field. So just as a side note, this is somewhat less important. If we look again at this equation for the potential difference, and we write down the units for this equation, it says 1 volt equals, and I'm writing here only the units. So something measured in volts equals this integral, which is a sum, and actually this sign for the integral exactly originates from the word sum, E, some units in which the electric field is measured. And in principle, we know that it's Newton per coulomb, but let me just leave it alone and write that as a notation for the unit of the electric field, multiplied by length, which is measured in meters. So I write 1 meter. And from here, it follows that the unit of the electric field is also 1 volt per meter. Well, we discussed before that the unit of an electric field is 1 Newton per coulomb, because it's of the amount of force per unit charge. So force Newton per charge per coulomb. But it turns out, now that we introduced volts, that 1 volt per meter is the same as Newton per coulomb. All right? And in the book, actually, before we covered that, perhaps you've noticed that sometimes units will be given in volts per meters. Well, let's do, if that makes sense, let's do a quick example. So let's consider a 9 volt battery, and those are these common batteries. Well, that's probably look familiar. So you see here, for someone it's extremely familiar. For someone, it's new. If it's new and if there's inscriptions looked mysterious in the past. Now I will demystify them. So, well, it says here 9 volts, and that's exactly what it also says here on each battery. And we now understand what it means. So each battery has got 2 terminals, plus, this is plus, and minus. And the purpose of this battery, when you plug it into a device, is to move charge from here to here. So that charge moves through an electric circuit and does useful work. And these 9 volts, that's the voltage difference or potential difference between these 2 terminals. It means that when moving 1 coulomb from here to here, when moving a unit charge, it will do 9 joules of work. But of course, it can move much more before it gets exhausted. And well, we can actually tell how much it will move. So 9 volts battery. The same statement could be made about other batteries. Just all of them have got 2 terminals, plus and minus. This is from where and to where the charge is moved respectively, and this one is 1.5 volts as it says here. But let's consider the this 9 volt battery, and before it gets exhausted, that is before it gets useless. Well, I'll write a particular brand. It's Duracell, and I promise that Duracell didn't pay me anything. It's not their advertisement in any sense. So it can move a lot of charge, 18,000 coulombs, before it gets exhausted, and it's really a lot. Later, when we introduce electric current, I can explain how to find this number based on milliamp hours that may be written on the packaging. But so far, let's say I looked up the specs of those batteries on the internet, and that's how much charge it moves from one terminal to the other. And we can tell how much work it does, because the potential difference is the work divided by charge. So the work it does, I'll write here, work it can do, it equals the product of charge and potential difference. So it's going to be 9 volts multiplied by 18,000 coulombs, and that's going to be 162,000 joules, so 162 kilojoules, and that's a lot of work, right? Just maybe we've got some sense of the amount of work from the classical mechanics class, Physics 5A. That's a lot of work. So that's how much energy is stored in a battery. Okay, does that make sense? Well, in reality, the voltage of this battery, it slightly depends on the amount of charge left. In fact, when it's completely fresh, the voltage will be slightly higher. It's going to be 9.6. Then, as you keep using it, it will drop to 9, and it will stay at a plateau of about 9 volts, but then it will drop rapidly once it's at the end of its lifetime, once it's exhausted. But to a good approximation, one can say that it maintains a constant voltage of 9 volts throughout its cycle of work. Okay. All right. If that makes sense, then we'll proceed to compute the potential difference around charged bodies. And what's the simplest configuration of charges one can consider? Perhaps it's a point charge. So I'll write here the potential, the electric potential of a point charge. So let's say we've got a point charge Q and we move a unit charge from point A to point B and then the amount of work done will give us exactly the potential difference. The potential difference between points phi A and phi B is going to be given by the integral of the electric field created by this charge Q dr. Well, I'll plug in the electric field of a point charge. It's going to be kq over r squared r hat. Now that's the unit vector that connects charge q to pointing from charge q to the point under consideration dr. And we've got to take this integral, but actually, pardon me, we took this integral last time. We had exactly the same integral, maybe with a different prefactor, just when we talked about the mutual change of the energy of two charges. Or the work done by one charge on the other. So it was exactly the same, but with a different prefactor. We had an additional prefactor, which was the value of the charge moving in the field of charge Q. So we know how to take this integral, and I'll just write down the answer. The result that we obtained last time. It's going to be kq, this prefactor, 1 over Ra minus 1 over Rb. And we see that the potential difference phi A minus phi B equals the difference of a certain function which depends on Ra and Rb. And here Ra and Rb are just the two distances. So we can define this function to be exactly the potential. So let us choose the potential at point A to be kq over Ra plus an arbitrary constant. And the potential at point B, the same with replacing A by B. And that constant can be arbitrary because when we subtract, when we compute the difference, it will cancel out. So, and well, that holds for an arbitrary point A, and therefore, for an arbitrary point R, for an arbitrary point distance R away from charge Q, write K Q over R plus constant. So right here, R is the distance to charge Q. So the potential at an arbitrary point is given, determined by the distance from that point to charge Q. And the choice of this constant is up to us. It's convenient to set it to 0, right? Yeah, 0 is my favorite constant. That would correspond to the vanishing potential at infinity. Meaning when R becomes very large, the potential vanishes. And yeah, that's the potential of a point charge. Let me actually put it in a frame, because that's one of those important equations that one's got to remember. A question?
Yeah, sorry, can you just remind me how the integral of kq over r squared r hat dr came out to be kq r 1 over ra minus 1 over rb?
Well, just very roughly, we first, so we've got an integral like this, r dr of r squared. I just rewrite this integral and I drop the constants of the prefactor. Then we can convert the product of these factors to scalars. So it becomes dr over r squared. And then we take this integral. So it's the integral of the function 1 over argument squared. This is minus 1 over r at the two limits, Ra and Rb, and that's how we get it.
So, sorry, I missed the first part of class. So just to clarify, we're talking about change in spatial location relative to a charge. So the charge itself is not moving, just the point we're looking at. We're looking at the change in potential, like the change in the electric field between 2 points, or the change in charge, or just to clarify.
Potential difference. So the charge, the probe charge moves from one point to another. We see how much work is done and define the potential difference.
Gotcha. So it's change in work between 2 points relative to a charge?
Yeah, it's, well, not change of work, just work to move the unit charge from one point to another. And that results in the change of energy of that charge in the field of charge Q. And now we set this constant to 0 so that the energy at infinity is 0.
Gotcha.
Right.
Thank you.
So when we take the integral and find that AQ solution, why do we jump to then choosing phi A equals KQ over RA plus
When we arrive at this expression, what we see is that it has the form phi a minus phi b equals some function. Let's call this function f. F of Ra minus f of Rb. And it just happens to have this form. We found this expression, and it just happens to be representable like this. And if that always holds for arbitrary Ra and Rb, then it's convenient to just say that phi a equals f of Ra plus a constant, and say the same thing about f of Rb. And yeah, that's what we did here. Okay. So that's the potential of a point charge, and well, very similarly, we can find the potential of multiple charges. Multiple charges. And well, because when charges do work, when other charges move in their field, and the respective forces add up, so do potentials. So if we've got multiple charges, Q1, Q2, Q3, and so on, Qn, somewhere here, and then they create some potential at this point, which of course depends on the point, and we can introduce distances to that point, r1 from charge 1, r2 from charge 2, Rn between this point and charge n. So we've got to add up their potentials. So the potential at this point is given by K, Q1 over R1 plus Q2 over R2 plus and so on, plus Qn over Rn. And that way we can find the electric potential of an arbitrary configurations of charges at an arbitrary point. Well, now we've introduced electric potential as a characteristic of the properties of the field. One might ask, do we actually need it? Because if we have a configuration of charges, we can in principle just find its electric field, and an extra characterization by means of the electric potential may seem excessive, because the electric potential can be found uniquely from the field. So why use the electric potential at all? And, well, one possible reason that comes to mind is that the description by means of the electric potential as opposed to electric field may be more convenient, because potential is a scalar, while the electric field of a system of charges is a vector. So instead of specifying a vector at each point in space, we can just specify a scalar function, which is less information and which does sound more convenient. However, if we specify the electric potential instead of electric field, do we by any chance losing information? And It turns out we don't. The electric field follows uniquely from the potential. Well, let's see exactly that. I'll write here the relation between electric field and potential. Well, in principle, we know that we already have some relation, so we know this formula here, and that gives some relation. So if we know the field, we can find the potential, but we want it the other way around. If we know the potential, can we find the field? And how can we find it, if yes? So, well, first, this is phi A minus phi B. Let me rewrite it as minus phi B minus phi A equals the integral from A to B E dot dr. Just to rewrite the same formula. Well, and let's apply that to an infinitesimal interval. Well, then there'll be no this integral, because our whole interval under consideration. Points A and B are infinitely close to each other. Our whole interval under consideration is one infinitesimal interval, and phi B minus phi A turns into the differential minus d phi. The differential is an infinitesimal change of quantity on an infinitesimal interval, and that equals E dot dr, and that allows us to find the electric field from the electric potential. So, it will be convenient to introduce some coordinate system x, y, and z. And if we consider dr, the displacement dr, parallel to the x-axis, meaning dr equals I dx, where I hat, that's the unit vector along the x-axis. Then minus d phi equals ex dx. And from here we can say that the electric field ex equals minus d phi over dx. So the derivative of phi with respect to x. Now, this notation, which I call d, is called partial derivative, and it may or may not look familiar, just depending on the prerequisite material. If it's not familiar, it's a very, very simple notion. The electric potential phi depends on three variables, x, y, z, on three coordinates. And this is called a partial derivative, meaning that we differentiate with respect to x only, as if the other two variables were constants. So basically it's the same derivative that you had before, it's just a different notation for it, just differentiate this with respect to x. And, well, the same formulas can be written